All right, so here we go. You can't see the title on this page, but it does say graphing cubic equations. It is lesson 5.3. Yeah, so if you're using the online textbook, look up Module 5, Lesson 3. We have, I need to fold my paper a little bit better because I can't see stuff there. It is? Okay. There we go. So there's lesson 5.3. And we have this thing called y equals x to the third. Can anyone see what it says before that? Mine's in the staple. Can anyone else see? Parent graph. Also known as the mother function. Get it? Parent, mother. Did you hear me say that last year, Abner? Yeah. So that is your original function. It is the function that has no stretches, no compressions, no reflections, no shifts in any direction. It is the absolute most basic form of that graph that you could have. Okay? So if we're talking about a cubic equation, that's a third degree. Yeah? Y equals x to the third would be the mother function for cubic equations. For quadratic equations, it would be y equals x squared. For linear equations, it would be y equals x. For seventh degree equations, it would be y equals x to the seventh, etc., etc. Okay? So it's your most basic one. It has what we call an inflection point. I'll talk about that in a minute. Yeah, before I get off to the rest of that, let's look at this really quick. You're familiar with this graph, right? Does anyone know what an x to the third graph looks like? It is a squiggle, if you want to describe it as that. Yep. An x to the third graph looks kind of like that. Okay? The way I picture it, let's see if I can do it on the screen here, is if this was a parabola, I need to zoom out. If this was a parabola and you took one side of that parabola and you flipped it upside down, that's how you get your cubic. Does that make sense? So if you took your parabola like this and just took one side and flipped it upside down, that's your cubic. Okay? And when you have your parabola, you've got a vertex right there, don't you? That point is still important. It's just called an inflection point, or a point of inflection now. Okay? So, not all cubics are going to be the parent function. Most cubics are going to be some kind of a transformation on that parent function. It's going to be taking that parent function and compressing it and shifting it and reflecting it and so on. Okay? And when we do that, we get this equation right here. Now, this equation should look pretty familiar. Yeah? There's two main differences between this equation and the one that you already know. What are those two differences? It's cubed. That's the first thing. And what?
A is multiplying into the thing. Wasn't it adding last time?
No, it was still multiplying, but that is where the other issue is. But what is the other issue?
There's a plus K.
Woo. The other one had a plus K. There used to be an F right there. Do you remember that? There used to be an F right there. Now, let me try and explain why this is different, why it doesn't have the F there. If I were to look back at yesterday's notes, we had a function and we called it f of x. F of x does not mean f times x. This is actually the name of this curve. You could name it Bob, you could name it Jane, or you could name it f of x. We named it f of x. Okay? In the same way that you would name your children different things, we name graphs different things. Because if we were all named George, it would be really confusing if I tried to say, hey George, what are you doing? Who would answer, right? So we have to call people different things. We have to call graphs different things so that you know what I'm talking about. So if I was talking about f of x, I would be talking about this one. If I was talking about g of x, I would be talking about that one. Does that make sense? Now, if we look at f of x, I don't know the equation of f of x, do I? I just know its name. So, when I fill all this information in, I have to write it all in terms of its name, f of x, because I don't know what its equation is. all of these cubics, I know what equation it's using. It's using this parent function, and it's just doing our transformations to that parent function. So I'm no longer using the name, I'm using the actual equation. That's why we don't need the F anymore. Okay? So two big changes, we don't have the F, we have a third degree right there. All right? This is the important thing, our inflection point. You have to find the inflection point first and foremost. If you don't find the inflection point, you can't do anything further with your graph. Your inflection point will always be H, comma, K. And you get that H and K from right here. Now, we have written down up here that the inflection point of the parent function is 0, 0. Why is the inflection point of the parent graph 0, 0? Well, what's the H value of the parent graph? 0. What's the K value? 0. That's why the inflection point is 0, 0. Okay? Does that make sense? All right. After that, we still have all the same letters we had before. A, B, H, and K. And I think the A is actually right in the hole punch right there. So, A, B, H, and K mean the exact same thing. So A is still a vertical, what is it? A stretch, compression, or a reflection. B is still a horizontal stretch, compression, or reflection. K is a vertical shift. And H is a horizontal shift. And it follows all the same rules as it did on that other page of notes. And when I say that other page of notes, I'm referring back to that one right there. Yeah? Okay, let me go back so you can write. Okay, so far so good? All right. Now, domain and range. I'm going to put the picture up here again. Here's our picture, looking at my x to the thirds. Did I put this up there before?
Yes.
Yeah.
I did put it up there. Okay. First off, let me talk about why this is positive x to the third and this one's negative x to the third. When you read a graph, you want to read it from left to right. I often think of it as though this is representing a hill that I'm walking on. If I were to walk from the left to the right, I may go down a little bit right here, but overall, I'm going uphill, aren't I? That means I have a positive A value. This one, if I start on the left and I walk towards the right, I end up going downhill overall. That's why we have a negative A value. All right? Now, let's just look at the positive A value one for right now. And let's think about domain. I have an arrow here, so if I were to ask you what's the furthest to the left that it goes, what does that arrow mean?
Infinity.
It goes to where?
Infinity.
Negative infinity. And I'm going to use that open parentheses, right? Because I can't use the bracket. And what about the furthest point to the right? Positive infinity, because it's got that arrow. What about range? What's the lowest point? Negative infinity. And the highest point? Positive infinity. Is that the same for the negative x to the third? Both of those are the same. One thing that is very, very handy is that all x to the third equations have the same domain and range, and it's always going to be the negative infinity to a positive infinity. What's another way of saying negative infinity to positive infinity?
All real numbers.
All real numbers. Okay. Starting tomorrow, you'll be able to use this notation. But for today, I want you to practice your interval notation a little bit more. Okay? All right. End behavior. I'm going to talk about this in a little bit, so I'm going to jump down to an example. Okay? So, we're going to graph the mother function. the parent function. What is my h value? Anything in parentheses with the x? Nothing, right? So h is 0. What is my k value? Also 0. So that makes my inflection point what? Oops, that's not what I wanted. 0, 0. We said that up above, didn't we? Well, now we reiterated it. Now, where does 0, 0 go? What do I do with that? Well, I have my XY chart there, and I'm actually going to highlight where it needs to go. Unfortunately, my hole punch strikes again. But 0, 0 needs to go in the middle of my graph, or of my XY chart. The reason is, on my graph, I want to know what's going on to the left and to the right. I want that inflection point to be in the middle, so it's got to be in the middle here. Okay? If I put it like at the top, I'm only going to see one side of my graph, and that doesn't really help me. All right. Now I need to come up with other x values. I want 5 x values with 0 being right in the middle. So I need to think, how am I going to count numbers with 0 being right in the middle? Well, one direction it would go 1 and 2. The other direction it would go -1 and -2. Doesn't matter if you put the negatives on the top and then the positives on the bottom. As long as they're all there, you're good. I would prefer you do the ones consecutively right next to them. Okay? It just helps you maintain a pattern there. Now, how do I find the y values? Plug them into the equation. So the equation is y equals x to the third. So if I plug in -2 and I raise it to the third, what is -2 to the third? -2 times -2 is +4 times -2 is -8. This one would be -1 to the third. What does that get me? -1. This was 0 to the third, but we already know that. 1 to the third. And 2 to the third. 8. So now I plot my points and connect the dots, right? Okay, so let's see. -2, -8 is all the way down at the bottom. -1, -1, 0, 0, 1, 1, and 2, 8. And then we play dot to dot. And finish it off with some arrows at the end. Yes? Right here? -2, I'm plugging it in right there, so -2 to the third power would be -2 times -2 times -2. You could also go to your calculator and do -2 to the third. Okay? Okay. All right. So let's talk domain and range. What's my domain? -infinity to +infinity. Again, you can get that from the graph, or you can get it from remembering that cubics are always the same. Range, also, -infinity to +infinity. Now we get to that stuff right here that's called end behavior. End behavior is exactly what it sounds like. How are the ends behaving? What's going on at the very ends of my graph? So these are kind of a complicated way of asking a very simple question. So, starting here, well, let me step back for a minute. This is 2 statements with a blank at the end, and that blank I have to fill in with either +infinity or -infinity. Those are my only 2 options. So let's see what this says. This arrow means as it approaches. That's what it translates to in math. So it says as x approaches infinity. Think about your x-axis. What side would go towards +infinity? The right side, correct? So that's saying look at the right side of your graph. Okay? The right side of my graph is not down here, it's up here. Do you get that? So on the right side of my graph, what is happening to y? Is it going up towards positive infinity, or is it going down towards negative infinity? It's going up, so I would fill it in with a positive infinity. So that statement says on the right side of the graph, the end is going up. What do you think the next statement says? Okay, so say that in regular language, not math language. On the left side of the graph, where is y going? Down. So I would put negative infinity. Kind of sort of makes sense? We'll be doing that for every graph we do for the next week or so. Possibly past there, I can't think of that off the top of my head. Okay? All right, next one. What is my h value? Positive 2. If you look up here, this is a positive h. That looks like a negative h, doesn't it? We always have to do the opposite when we're dealing with h. K, sign is positive there, and here k is always going to be the same. So h looked like a negative 2 there because it was a minus. We'd call it a positive 2. What is my k value? 0. There is no k value because there's nothing hanging out there. What's my inflection point? 2, 0. And I'm going to put 2, 0 right in the middle there, yeah? Now, how do I come up with x values around there? Because I can go 1 and 0 on one side, 3 and 4 on the other side, because I need my 5 numbers counting with the 2 in the middle. Again, doesn't matter if you put the 1 and 0 on top and the 3 and 4 on the bottom, as long as they're all there. Now what do? Plug it in. So negative 1, parentheses, 4 minus 2 to the third. Now I'm going to show you how to do this on your calculator. So if you have your calculator, take it out, because your calculator actually makes this easier. What? A calculator makes math easier?
You had a substitute that she was born BC before calculator.
Was that Miss Gaines? That sounds like something she would say. Okay, so I'm going to plug this in. The first time you plug this in, you're going to want to plug it in very carefully. And almost any calculator can do this. Yours might have slightly different values than mine, or different buttons. But plug in your negative 1, parentheses, 4 minus 2, close your parentheses, do your exponent button, which on this calculator is that X with the box. On a lot of calculators, it's a little button that looks like this. That's your exponent button. Okay, and let's see, to the third power, and hit enter, and I get negative 8. Let's check that. 4 minus 2 is 2, to the third is 8, times negative 1 is negative 8. Okay, so I know I put it in right. Now, I don't want to have to retype the whole thing in to put the 3 in. Do you want to see how to do that? You want to arrow back. What is it that you need to change to a 3? The 4. On this calculator, you go right to the 4, and you hit delete. If you have one of those Texas Instrument ones, like this one, you have to highlight that number. Go to where it's blinking on that number and just press 3. Hit enter again. It's doing all the work for me. Okay, work smarter, not harder. Go back. Got to change the 3 to a what now? I don't need to do a 2. I already know the y value. 1. Positive 1. And then 0. That makes it go a lot faster, doesn't it? The trick is you got to make sure you typed it in correctly, because if you typed it in incorrectly, all those are going to be wrong. Okay? So use your calculator to save yourself some time. You are smart enough you could do that by hand if you needed to, but save yourself the time. Okay? So now let's plot our points. 4, negative 8, 3, -1, 2, 0, 1, 1, and 0, 8. And then do your dot to dot. With just as smooth of a curve as you can. Did you notice that the y values were the same as the y values over here? If you flipped your chart upside down, they could be in an opposite order, but they're the same y values, aren't they? The same exact numbers, which means that there's nothing going on vertically. There's no shift, there's no compression, there's no stretching, there's none of that. There could be a reflection, which there is in this case, but there's no shifting or compressing or stretching with those y values. All right, what's my domain? Negative infinity up to positive infinity. What's my range? Negative infinity to positive infinity. Okay, now let's talk end behavior. What is the first statement telling you to look at? The right side, because x going towards positive infinity would be on the right side. On the right side, what is my graph doing? It's going towards negative infinity. Okay, as x approaches negative infinity, what's that asking about? The left side of my graph. It is going up towards positive infinity. And check this. Sometimes, if you're looking at the book, they might have the left side written first and then the right side. Just make sure that you read it to make sure that you're getting it straight. Okay? All right, you try setting up your point of inflection here. Try coming up with your H and your K and setting up your point of inflection. What's your H value?
0.
What's your K value?
1.
So what's your point of inflection?
0.
0, 1. Now, does the chart bother you at all?
Yes.
It bothers me because there's no middle like there was up here. But that's kind of intentional. I'm going to put mine right here. It's not a huge deal if you put it one up or whatever, as long as it's somewhere in the middle. And there's kind of a reason as to why there's a strange number of spots there. And it has to do with the fact that this right here is a fraction. And what do we know about fractions? They're frustrating to multiply by because they don't make everything a nice number, right? They change nice numbers into ugly decimals. So if I were to think about this and do my typical -1, -2, 1, and 2, I might encounter some decimals as I figure this out. So let's try, I'm going to start with -1, just below here, and I'm going to plug it in. So let's see, 1/2, use that fraction button on your calculator, times -1 to the third plus 1. I have a fraction, or some of your calculators may give you a decimal. I don't want to graph a decimal. Because if I start graphing decimals, I'm going to start seeing only a very skinny part of my graph, and I'm not going to see the ends. So I don't want to use -1. Crossing it off. Let's try -2. I can arrow back and change that -1 to a -2. Let's see if that has the same problem, or does it give me a nice number? Oops, 21's not going to give me a nice number. But how about -2? Does that give me a nice number? It does. So -1 didn't work, -2 does. Do you think -3 works? Well, it's easy for me to check. Just change it to a 3. Nope. So what do you think I should try? -4. It's a big number, but it's a nice number. So I want to stick with nice numbers. Why is it negative 31? Well, what's negative 4 to the third power? Negative 64 times 1/2 is negative 32, plus 1 is negative 31. Okay? Let's try the other side. Is positive 1 going to work? Probably not. Nope. Is positive 2 going to work? Yep. So I'm going to change that to a 2. And let's see, it gives me 5. And I think the next one that's going to work is 4. Why do you think I have all these even numbers? Because even numbers cut in half nicely. Just to show my point, 3 doesn't give me a nice number, but 4 does. Gives me 33. Okay? So, I can't plot negative 4, negative 31 on my graph, can I? My graph doesn't go that far. I could extend my graph and make a really awkwardly big graph if I wanted to. Or, let's start off just by plotting the numbers we can. So negative 2, negative 3, 0, 1, 2, 5. And remember how I said you're always going to have these 3 points in the middle and then you'll have 2 outsiders? These are the 3 points in the middle for this graph because they were the 3 points in the middle right there. The 2 outsiders. Now, I can't just go off the edge here. I can't just continue this and go off the edge. Why? Well, because if I continued it and went off the edge, that would be implying that like negative 4, negative 5, or negative 4, negative 6, somewhere in there was actually on the graph. Is negative 4, negative 5 on the graph? Or negative 4, negative 6? No. Negative 4, negative 31, somewhere all the way down here is on the graph. So I can't cross that negative 4 line until I've gone down 31 spots. And I'm not going to go down 31 spots. So I'm just going to say that it's heading that direction. Does that make sense? Yeah. Same thing on the other side. I'm not going to go all the way up to 33, but I'm going to show that it's not going to cross that line at 4. It's heading up towards 33 where it will cross that line. Okay? Now, real quick, before we do domain and range, I'm not going to have time to do this problem, but how is this equation different than this one? It's negative, which means we have a reflection. Since this is in parentheses, this is a B value, whereas this was an A value, which means you're going to have a stretch or a compression in a different direction, right? But the main thing I want you to remember is when you come up with your X values the same way, this one you have to multiply X by the 1/2 before you raise it to the third power. This one we raised it to the third power and then multiplied it by 1/2. You do have to follow PEMDAS as you're doing that. All right, let's finish up here. Domain, negative infinity to positive infinity. Range, same for range, negative infinity to positive infinity. And end behavior. First statement is asking about what, the left or the right? The right. Whenever it says X to positive infinity, that's to the right. So where does Y go? Okay. And on the left, we are going towards negative infinity. Okay? All right.